What is up, young chemist? Mr. Rosen here. How's it going? Today we're going to be talking about isotope notation and average atomic mass. We're going to talk about how to calculate average atomic mass. This is in our unit exploring the parts of the atom, the subatomic particles, and structure of the atom, as well as the periodic table. So we're going to start by thinking about these subatomic particles, protons, neutrons, electrons in an atom. And we're going to represent some of that information using what's called isotope notation. It's kind of a shorthand or convenient way to show information about how many protons or neutrons or electrons a particular atom has. So there's some text here. You can pause it and read it if you would like to. But the atom has a center, what's called the nucleus, and the nucleus contains both protons and neutrons. In the space around the nucleus, you have electrons, making up what's called the electron cloud. And the electrons are at sort of specific or different distances from the nucleus and different regions of the space around the nucleus. So, a couple of terms here. Atomic number is the number of protons. Okay, atomic number is equal to the number of protons. That's in the nucleus. The atomic number, which is the number of protons, is how the periodic table is arranged. So, element number 1 on the periodic table, hydrogen, it has the atomic number 1. That's because it has 1 proton in its nucleus. Helium is number 2 on the periodic table. It has the atomic number 2, and that's because a helium atom will have 2 protons in its nucleus. And you can just increase by 1 proton each time until, as of today, we have 118 elements, which means we have 118 protons in the atom of the largest element. Each element has a different number of protons. That's what gives it its identity. Now, mass number is the number of protons plus neutrons. Okay. Almost all of the mass of the atom is coming from the protons and the neutrons. The electrons do have some mass, but it's very, 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 very small. It's about like a proton is a little less than 2,000 times as heavy as an electron. It's like 1,840 times as heavy as an electron. So the electrons, even if you have like 50 or 60 electrons, that mass is very, very small. And for our class, we're not going to take it into consideration for calculations. Now, if you're going to have a neutral atom, which means no charge overall, the number of protons is going to be equal to the number of electrons. Protons have positive charges, electrons have negative charges. So if those two are equal, then there's no charge overall. An ion is a particle that has an overall charge. So it's going to have an overall charge if you have a different number of protons than electrons. In chemical reactions, we're dealing with electrons being gained or lost to take on the charge, and we're not really dealing with proton changes. In our unit on nuclear chemistry, we'll talk about changes in the nucleus a little bit, but for chemical reactions, the nucleus is not involved. Okay, so this is an example of isotope notation. You have the element symbol. In the bottom left, there's the atomic number, which is often written or symbolized as Z. That's atomic number. And you also have mass number, which is sometimes, abbreviated as A. Again, mass number, this is protons plus neutrons. And then sometimes you have a number up here, which is the charge. Now, if there's no number written there, that means it's neutral. And that means that your if it's neutral, your number of protons will be equal to the number of electrons. If there's a charge, you have to think, does that mean we have an excess or more electrons or more protons than electrons? You can also use the periodic table to help you do a lot of this. So we're going to do some examples here, and the first ones, there's nothing written, but you're just going to look at the periodic table. You do a little bit of estimating or rounding to find out about the other parts, but you also need to look at a periodic table to answer some of this. Okay, so if you want to, you can pause the video and fill out some of this box and then watch me as I go through. Okay, so the first one on here, it says helium, atomic number, average atomic mass, all that. So I'm going to bring in a periodic table here, and looking at it, helium is right here. Now, the atomic number on this periodic table is the number on the top, so it has the atomic number 2. So atomic number 2. Average atomic mass here is listed at 4. Now, mass number, we're just going to base our mass number on taking the average atomic mass and rounding it to the nearest whole number. So, unless a mass number is provided, we're going to just use a periodic table and round the average atomic mass to the nearest whole number. So if we know the atomic number is 2, that's the same as the number of protons. That's just sort of a definitional thing, right? The atomic number is the number of protons. So if the atomic number is 2, the number of protons is 2. Now, the mass is 4. And of that 4, 2 of it's protons. And the mass comes from protons and neutrons. So if 2 of the 4 are protons, the other 2 have to be neutrons. And because you can see that there is no charge written here, if we have 2 positive charges, we also have to have 2 negative charges in order for this to be a neutral helium atom. So you're kind of using a little bit of logic as you do this. The next one on here is Br. So we're going to find a Br on the periodic table. It's right here. It's element number 35. So the atomic number is 35, and the average atomic mass is 79.9. So the atomic number is 35. The average atomic mass is 79.9. So for a mass number, I'm just going to go to the nearest whole number. So we'll say that for this atom, probably the most likely isotope that it is the mass number 80. So if the atomic number is 35, that means the number of protons is 35. And also, just to jump ahead, you can see that this is a neutral compound. If this is neutral and we have 35 positively charged protons, we have to have 35 negatively charged electrons. Those are going to be the same for each neutral atom. Now, in terms of figuring out neutrons, in the first example, these were the same numbers. So you might be thinking, well, is this also 35? Nope, it's not. Because if you look at the mass number, it's 80. Protons plus neutrons give you your mass number. We have 35 protons. So you have to think, 35 plus what gives you 80? And the answer is 45. 35 plus 45 is 80. Okay? For the first maybe 20 elements, you often have a 1-to-1 ratio of protons to neutrons. But once you get above element 20, you start to have more neutrons than you have protons. And it becomes more dramatic the higher up you go. And that has to do with the stability of the nucleus. Okay, so let's do some of the ones here where information is provided. So if we have a number in the bottom left here that's a 6, that's the atomic number. And if you want to look on the periodic table, you can see that carbon is number 6. So just jumping ahead, if it's atomic number 6, that means the number of protons is 6. And you can see that there's no charge, so that means that the electrons are also 6. Now, the mass number is written right here as 14. The average atomic mass, you have to look on the periodic table for. Okay, and carbon is right here on the periodic table, number 6. It has an average atomic mass of 12.01. So in this case, you can see that the isotope that we have is higher than the average atomic mass. Now, just to, I guess, refresh your memory, an isotope is when you have atoms of the same element that have different masses. And they have different masses because they have a different number of neutrons. Right? So if they're atoms of the same element, by definition, they have to have the same number of protons. So, carbon, you might have C12, you might have C13, or you might have C14. These are all mass numbers. So if you had a sample of carbon, some of them would have 6 protons and 6 neutrons, some of them would have 6 protons and 7 neutrons, and some of them would have 6 protons and 8 neutrons. So notice they all have 6 protons because they're all carbon, but they have a different number of neutrons, and that means that they have different masses. So in this case, we have a carbon-14 atom. It has 6 protons and 8 neutrons. Okay, continuing along. I'm going to go a little bit faster on these ones. Lithium has the atomic number 3. That means it has 3 protons. Now you can see that it has a positive charge. So you have to think. If this had 3 protons and 3 electrons, it would be neutral. So if it has a positive charge, does that mean that it has more electrons than protons or more protons than electrons? If it has an overall positive charge, that means that there are more protons than electrons. So that means we have to have only 2 electrons, right? If you have 3 positives and 2 negatives, overall it's going to have a positive 1 charge. The mass number is given here as 6. For the average atomic mass, you're going to look on the periodic table, and lithium on the periodic table, 6.94. These are in atomic mass units. If the mass number is 6 and the protons are 3, then the number of neutrons is also going to be 3. So this is our first one that had a charge on it. It's a little bit different because the protons do not equal the electrons. Now this one doesn't have a charge, so its atomic number is 17. That means its number of protons is 17. That means the number of electrons is 17. The atomic number, is 17. The mass number is 35. If you look on the periodic table, chlorine is number 17 right here, has an average atomic mass of 35.45. All right. Neutrons is going to be 17 plus what gives you 38. 17 plus what gives you 35. And the answer there is 18. 17 plus 18 is 35. Okay, last one. Sodium has an atomic number of 11. That means it has 11 protons. Now this one, again, is a positively charged ion. So that means it has 1 more proton than electrons. And if it has 11 protons, that means we must have 10 electrons. The the mass number is 23. If you look on the periodic table for sodium, the average atomic mass is 22.99. So our mass number is very close to our average atomic mass. And you have to think, something plus 11 gives you 23. And that something is 12. Okay? So this is some practice, interpreting isotope notation. What are the different parts? How many protons, neutrons, electrons does it have? What's its average atomic mass? That kind of thing. So now we're going to answer some questions and maybe even practice writing isotope notation. I'm going to zoom in on this part. You can, if you want to, you can pause the video and try to answer these questions. And then I'm going to go over the answer. Okay, so number 1 says, give the correct isotopic notation for copper 63. So we're going to be writing something like this for copper 63. And when you write something like this, earlier I did carbon, this is the mass number. 63 is the mass number. Now it's copper. Copper has an element symbol Cu. 63 is the mass number, so that means that a 63 goes up here. And the fact that it's copper means we can look on the periodic table and see what its atomic number is. Its atomic number is the number of protons, which goes in the bottom corner here. Now, copper is number 29 on the periodic table. It's right here, 29. That's its atomic number. That means 29 is the number of protons that it has. So that means that a 29 is what's going to go here. So that's our correct isotope notation. This one says calculate the total number of neutrons in an atom of sulfur 32. So sulfur 32, the isotope notation would look like this. If you find sulfur on the periodic table, it's element number 16. Okay. So if it's element 16, that means it has 16 protons. If its mass number is 32, that means 16 plus what gives you 32, right? The mass number is protons plus neutrons. This is asking for how many neutrons it has, and we know that it's element number 16 because we can look right here on the periodic table and see that sulfur is element number 16. That means it has 16 protons. And the answer is 16 plus 16 is going to give you 32. So 16 is how many neutrons that has. I actually answered this question earlier, sort of by accident. It says, how do the nuclei of carbon-12, carbon-13, and carbon-14 differ? So they're all carbon. Carbon is element number 6. That means it has 6 protons. If you have carbon-12, that means it has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons. And then carbon-14 has 6 protons and 8 neutrons. So they're all carbon. All of these nuclei have 6 protons in them, but they differ by how many neutrons they have. This has 6 neutrons, this has 7 neutrons, this has 8 neutrons. These are called isotopes. They're different isotopes of the same element. They're all carbon atoms, but they have different masses because they have a different number of neutrons. Okay, consider this isotope symbol. Now these two numbers should be on top of each other, but I was using Microsoft Word and I couldn't figure out how to do that, so they're just slightly next to each other. But what does the superscript 195 indicate? That is the mass number, which is protons plus neutrons. I'm zooming out so that you can see that. Sorry. Okay. And then this one says, what does the subscript 78 indicate? That is the atomic number, which is protons. And if it was a neutral atom, that would be the same as electrons, but that's not necessarily always the case. This one says, how many neutrons are in a platinum 195 nucleus. So if it's 195 and then this is 78, right? This is our number of protons. This is protons plus neutrons. So you think 78, that's an 8, plus what is 195? Right? 78 plus what is 195? So bring this in. 195 minus 78. 117. That is your number of neutrons. 78 protons plus 117 neutrons gives you your mass number, 195. Okay, so far we've been thinking about and digging into the parts of the atom, the idea of isotopes, protons, neutrons, electrons, average atomic mass, mass number, atomic number, that kind of thing. This column right here is average atomic mass, and these are just getting pulled from the periodic table. Now you might be wondering, where do these numbers come from? How do we get these numbers? Another thing to think about is, why are these not, like integers? If we're looking at our number of protons and number of neutrons, if you add those together, you should get integers, right? Whereas these have decimal points and numbers after the decimal point. So these are called average atomic masses. And the reason it's an average is because, like, if you consider this example here for carbon, if you have a sample of carbon and you were to be able to look at one atom in the sample, most of them would be carbon-12 atoms, meaning most of the carbon atoms would have 6 protons and 6 neutrons. But some of them would have 6 protons and 7 neutrons, and some of them, even smaller, would have 6 protons and 8 neutrons. Now, the mass of any one isotope, right, is right here on these integers, but if you were to average these, you might say, okay, well, if I average 12 plus 13 plus 14, then I divide by 3, I would get 13. And that would be true if we had the same amount of each of these. But if you have a sample of carbon, almost all of it is carbon-12. A very small amount of it is 13 and 14, which is why the average is basically 12. It's a little bit higher than that because there's a really small amount of these two isotopes. So the average atomic mass takes into account not only the mass of the individual isotopes, but also the abundance of each isotope, meaning how much of each isotope you have in a sample. And we are going to be practicing actually calculating average atomic mass. So what it says here is, when calculating average atomic mass, you need to take into account both the mass of each isotope and the abundance of each isotope. So here's an example. It says silicon is found to have 3 isotopes. Incorrect use of there. Their abundance is, I copy pasted this problem, so that this is doesn't make a lot of sense, but okay. Si28 is 92.23. Si29 is about 4%, and Si30 is about 3%. So if you had a sample of silicon and you analyzed it, these are the percents of each isotope. So it says calculate the average atomic mass. Now you can do this a couple of different ways. One way you can do it is just leave the percents as is. So if we have Si28, we're going to say 28 times 92.23. We have 29. So that's going to be times 4.67. And then we have 30, which is going to be times 3.10. Now, if you add the percentages up, they should add up to 100. Okay, and just sort of eyeballing this, it looks like it should be 100. Now, if you do the math on each of these, we're going to have 28 times 92.23. I'm just going to write down what my calculator gives out for each of them. $135.43. That's a 3, sorry. And then 30 times 3.1. We get 93. Okay, so we took the mass of the isotope and multiplied it by its abundance. I'm now going to add these all together. Okay, I'm going to add these all together. So 93 plus 135.43 plus 2,582.44. So I add them all together, and what I get is 2810.87. For the sake of this video, I'm just going to be treating these as exact numbers and using these for the sig figs. So this has 4 sig figs, 3. This had 3, and then I added them together, and this has 1 number after the decimal point. So this could have 1. It's not really going to matter though, because these were percents, right? Like 992 or whatever. And hopefully you look at this and just say, wait, hold on. Our average atomic mass is 2,800. That doesn't make any sense. I left these percentages as is, which means at the end, you need to divide by 100. And if you do divide by 100, you would get 28.1 and 28.10. This is our AMU. This is our average atomic mass. So we added them together and then divided by 100. And if you look at this, your average should be between, we have 28, 29, and 30. Your average is between 28, 29, and 30. And it's closest to 28, which makes sense because that's the most abundant isotope. Often, your average atomic mass is closest to the mass of the most abundant isotope, right? 92% of it is 28, so it should be pretty close to 28, but there's a little bit that's 29 and 30, which is why the average gets pulled up. Okay, now, in this, I left the percents as is, and then I divided by 100 at the end. You could have this as 0.92, and this as 0.0467 and 0.031. You can divide the percents by 100 at the beginning, and then you do the math and you just add them together. Or you can leave them as is. So you're either dividing by 100 at the beginning, or you're doing it at the end. Either way, you'll get to the same answer. You can decide which one you want to do. Okay? So this is calculating average atomic mass. You multiply the mass of the isotope by its abundance, add them all together, and then divide by 100 if you didn't do it to the percents to start with. So Here are a couple of problems. I guess I'll leave these two up here so you can see them. If you want to pause the video and try these, go ahead, and I'm about to work them out. Okay, so in this problem, you have the mass of the isotope and its abundance. So I'm just going to multiply these. Okay, you can kind of just, or this. So I'm just going to multiply all of these and write down what my calculator gives me. 0.050 times 234. 1.17. And then I'm going to go 0.72 times 235. So 169.2. And then 99.275 times 238. So hopefully you can recognize right away this is 236 27.45. Hopefully you can see right away if 99.275% is 238, your average should be very close to 238. Okay, it's going to maybe be pulled down just a little bit, but it should be very close to 238. Now I'm going to add these together. Um, 169.2 plus 1.17. This gives 2379782. Now, this has to be divided by 100. And if you do, you get 237.97. And yeah, this is I just, we could do some different rounding, but I just want you to see that this would be a little bit less than 238, very close to it, and the average is brought down by these lighter too. All right, let's do this next one. So it's sulfur. It says 95% have a mass of 32, so we're going to go 32 times 95. And then it says 33 is 0.76%, and then 34 is 4.22%. So we're going to multiply those. Sorry. 32 times 95, 3040. 33 times 0.76, 25.08, and then 34 times 4.22, and that's 143.48. Now I'm going to add all these together. I'm going to add these together and see what we get. get 3208.56, 3208.56. Okay, now that number is going to get divided by 100, and you get 32.08. Now we can look on our periodic table. It should be pretty close. And then again, the isotopes are 32, 33, and 34, and this is between them, and it's closest to 32 because that's the one that we have the largest percent of in terms of the mass. Okay, final problem here. This one has more isotopes. Pause the video and try to do this one on your own, and then you're going to check your answer. Okay, go ahead, solve this for chromium. Okay, here we go. I'm going to multiply these and write down what we get for each one. All right, and I'll just put this off to the side here. 50 times 4.35. My hand's in the way. 217.5. We have 52 times 83.79. That's 4357.08. We have 53 times 9.5. That's 503.5. And then we have 54 times 2.36. That's 127.44. Okay. We're going to add these all together. Okay, and what the calculator gives is 5,205.52, 5,205.52. You're going to take this divided by 100, and you get 52.0. I guess I'll just round to 06 AMU. And if you look on the periodic table, the average is pretty close to 52. And 52 is in between 50 and 54, so that makes sense. It's also closest to our most abundant isotope. Almost 84% is 52. Almost 84% is 52, and our average is very close to that. It's pulled up. It's pulled up a little bit more than it is pulled down in this case, and we get our average. So this has been some practice calculating average atomic mass. That's based on the abundance of each isotope. We have also thought about isotope notation, differences in isotopes in terms of protons, neutrons, and electrons, and how to express that using isotopic notation. As with all of our chemistry work, make sure that you are doing practice problems, doing the practice quiz or test questions at the end of your lesson. Keep up the hard work. Study, study, study. Let me know if you need anything. This is Mr. Rosen. Out.